Hello everyone and welcome to this video. In this video I'm going to do my first frame example, and the problem I'm going to solve is this one shown here, where I have two frame elements with fixed ends at node 1 and a roller support at node 3, as well as applied loadings at node 2. And you will notice both elements have length of 4 meters and the section properties and inertia is given there. The Excel sheet I have open here is the one I derived in my template video. Basically all this thing does is I input my parameters here, my section parameters, the length of my element, as well as the angle it's rotated, and then it calculates the element matrix for me automatically. And the sketch up here is just how the element looks, and also indicates the positive sign conventions as well as the degree of freedom. Okay, so yeah, let's get started. So first thing what I want to do is get my element matrices for element 1 and 2. This will be obtained by entering my parameters here. So the area of both elements are 4 times 10 to the minus 2. My E modulus is 70 gigapascals, so that's 70 E9. My inertia is 2 times 10 to the minus 4. And length will be 4 meters for both elements. And I'm firstly going to start with element 1, and noting on the measurement of theta, you'll see it's from the horizontal measured positive upwards. So for element 1 shown in the sketch, theta will be 90 degrees. So I'm going to put in 90 degrees, and there's my element matrix. So I'm just going to copy that. So I'm going to name that element 1. Select that, copy, paste those values. Okay, so I always like to label my degrees of freedom on my matrices, so I know which values correspond to which degree of freedom. The way I do that is, as in the way of deriving this matrix, I just write the degree of freedom on top. So it will be, for element 1, taken the node 1 to node 2, it will be U1, V1, Phi1, and then U2, V2, and Phi2. You're going to put some color there so I know which is my labels and which are actual values. These degrees of freedom are also going to be used when I assemble my global matrix, and I'll show you that in a moment. Okay, so this is our first matrix, or first element matrix. You will see the U1 corresponds to the horizontal displacement at node 1, and V1 vertical displacement, and Phi1 rotation, and the same for the second node. Okay, now I want to assemble my element matrix for my second element. So I'm just going to copy all this again, because it's basically a repeat of what I've just done. And I'm going to paste it right about here. Just paste it. And I'm going to delete those values because we're going to have our new values inserted there. Okay, so you'll see element 2 is horizontal, so the angle or theta will be 0 degrees, and that's the only difference between the two elements. So again, just copy my values there. Paste my value over there. Maybe I'll change that to 2, so that is what it is. And for element 2, my degrees of freedom will also change. And for element 2, it will be from node 2 to 3. So that will be U2, V2, Phi2, and U3, V3, Phi3. And I have to make that correspond to my rows. So I'm going to say copy and paste transpose over there, and now that's also correct. Now the next step is assembling my global matrix. Now what this is basically doing is I want to combine these two into one big matrix, which entails, or which has inside it, the degrees of freedom from V1, Phi1, U1 up until node 3's 3 degrees of freedom. So I'm just gonna write k global equals, and I'm not going to do this by hand. I'm going to show you how to do this automatically in Excel, because to do it by hand is quite tedious, and when you have more elements, for example 3, 4, 5 elements, this becomes quite big. So I'm just going to label my degrees of freedom. So I'm going to start with node 1, node 9. I always start, sorry, I just got a bit confused there. I always start labeling my unknown displacements or my unknown degrees of freedom first, because those are the ones I want to solve first. So I'm going to bring the problem down so I can see. So you'll see node 2 is completely unconstrained. So these displacements at node 2 is what we want to determine, for which the degrees of freedom there is unknown. So I'm going to start off with those. So I'm going to start off with v2, v2 and phi2. And other unknown displacements will include the horizontal displacement at node 3. So I'm going to type in u3, and the rotation at node 3 is also unknown, so that will be our next entry. And then we just continue with our constrained or fixed degrees of freedom, which will be the entire node 1, that will be v1, v1, phi1, and lastly the vertical displacement at node 3 is also fixed. So again, I'm just going to make that a color, and again copy that and paste the transpose of that. Okay, so now basically what I want to do, I want to do an index type of lookup, or VLOOKUP combined with another method. I'll show you now, to compile this big matrix by looking at both these matrices. For example, the first cell U2, U2, it must go and look for U2, U2 in this matrix, that will be that 2625, and then add that with U2, U2 in this matrix, which is that 7. Now how you do this, you type equals if error, and then the value is VLOOKUP, and you must look up that value in that array. Select that. You can select the top part as well, but it wouldn't make a difference. And then for the column index, you'll type match, and lookup value will be the column index, and then lookup array will just be that top row of the element matrix, and the max type should be exact, so just type a 0 there. Then the VLOOKUP should also be an exact match, and if error, value if error is when these values are not found in this matrix, it should give me a 0. This should be quite clear. I've also made a video where I have explained this, so you can check that out if you want to. Okay, next, before I get to my second element, I want these references to always stay the same for this matrix when I drag it through and down for the entire matrix. So my arrays, I just press F4 to fix them completely. You can see it adds the $ automatically. And next, my row number or row degree of freedom will always be in column D in Excel, so I can just put a $ before the D, and then this row or this entry will always be in row 63, so I can put a $ before the 63, and then I have fixed everything. So that is my completed statement for the first element matrix. Now I want to do it again for my second element, so I say plus, and you can type it out again, but I just like to copy the entire thing, copy and paste, because those references stay the same. The only thing that must change is my element matrix references. So I'm just going to select my element 2 as a reference this time. Remember to press F4 and fix both of them, and then again my column entries, and that's basically it. Just remember always, these two reference arrays must start at the same or in the same column, otherwise it will give wrong references and you'll get a wrong global matrix. Okay, so I'm just going to press enter, and then all that's left is to drag it to the right and then drag it downwards. And I have clearly done something wrong. Let's just have a look. Ah, you see that thing is not fixed. Okay, let's just correct that. I forgot to fix that column. So press F4, F4. See what happens when you don't fix everything. You get zeros everywhere, and this should indicate that you did something wrong. So if you get something like this, you probably forgot to put your references correctly. So let's try this again. That stays the same, and now we have values everywhere. If you have zeros like this, these are fine, because when you're looking at U3 and Phi 3, U3 and Phi 3, they are 0 in this element matrix, and it's not present in this one, so that should be a 0. Okay, so it's safe to assume I have assembled my global matrix correctly. Okay, so the next thing I want to do is write my matrix equation. So the general equation looks something like this, where my force vector is equal to my global matrix multiplied by my displacement vector. Okay, and this is basically what the stiffness method is about, and now I'm just going to write that in matrix form. I'm going to say matrix equation, and my force vector is basically just the applied forces, but firstly I'm going to copy my global matrix. I'm going to say copy and paste it, let's say there, doesn't matter. I'm going to place links this time, because when I change something here or add an element or something like this with different element properties, then I can just change these two matrices and it will automatically correct itself all the way through. So again, I'm just going to add my colors there, so know which are indices and which are not, and add my multiplication operator. Okay, so for my force vector, I'm going to look at the sketch and see which forces apply to which degree of freedom. So it's also nice to remember each row is corresponding to the specific degree of freedom associated with it. That's why I like to keep my labels with my global matrix, so I can know which row corresponds to which displacement. So the applied force in the vertical direction at node 2 is the 20 kilonewtons to the left, and that will be minus 20,000 in this case, because it's to the left, it's minus or negative, and kilonewtons is 20,000 newtons. I always work in newtons and meters, it keeps it quite simple, and yeah, it's always easy to convert the answers to millimeters or kilonewtons again. Okay, my applied force to my vertical displacement at node 2 is 0 newtons, and my moment at phi 2, or my applied moment, is 30 kilonewton meters, so that'll be 30,000 positive because it's anti-clockwise and that's a positive sign convention. U3, the horizontal load applied at node 3 is also 0. Phi 3 is also no moment applied there. And at U1 there will be a reaction which we want to solve, so I'm going to say horizontal reaction at node 1, and vertical reaction at node 1, moment reaction at node 1, and vertical reaction at node 3. So what I want to solve later on is these reactions as well as my analytic displacements, which is in my displacement vector. So for my displacement vector, I'm going to copy these. I'm going to place values, that's easiest, and my unknown displacements are all the displacements at node 2 as well as those 2 at node 3. So those are kept unknown, and these are all 0 because they are fixed or constrained degrees of freedom. Okay, so this is my matrix equation written down nicely. I always like to color code my matrix because I'm essentially going to solve two equations. First one is going to be the top one, and the second one is going to be the bottom row. And for that, I like to color code my global matrix or my global matrix in my equation. So it's how many zeros do I have? Yes, that will be that much. I'm going to make that something like this, something like that. I'm going to make that pink. I'm going to make that green, and can make that neutral. Doesn't really matter. This is just easy to visualize and know which part of the matrix you're working with when, because basic matrix calculations is this. Let me just select the entire thing. So these forces, or this part of the force vector, will be equal to that part of my global matrix multiplied with that part of my displacement vector, and the pink part of my stiffness matrix multiplied by the zeros in my displacement vector. I'm just gonna copy in some, or the basic theory around this matrix calculations. I mostly explained this now, but just that you have something as a reference when you're looking at this Excel file, because I will make it available to you. This is basically what I explained now. That must just not be like that, so you can see what is actually standing there. Okay, so the force vector 1 is going to be the stiffness method free, or KFF, times the first part of the displacement vector added with KFS multiplied by the second part of the displacement vector. Okay, and when you rewrite the first equation, I'm going to fix that as well, you get something like this. Then you can see KFF times D1 is equal to that, and thus D1, which is my unknown displacement part of my displacement vector, equals the inverse of KFF multiplied by KF1 minus KFS times D2. Now D2 in this case is all zeros, so we can ignore that part of the equation. So now, in order to solve our displacement, we do the following. I'm going to write displacements, copy my unknown displacements from there, paste. And then I select the correct size of my matrix and say equal matrix multiplication, and I want the inverse, which is M inverse, of the green part of my global matrix multiplied with my known part of my force vector. And then hold Control and Shift and press Enter, and we've solved that part. And just to add some units so we can orientate ourselves, that'll be meters, radians, meters, and radians. I'm going to say that is equal to that multiplied by 1000 millimeters, and that is going to be this one as well as for that one. Okay, these are displacements in millimeters. See how easy it is to convert your answers to different numbers or different units to make it more indicative. So that's something like this. And then next I want to solve my reactions. I'm going to label that reactions, and my reactions will be that part. Let's say copy, paste, then put my equals in, and then again select the correct size of the matrix, then that is going to be equals matrix multiplication. The bottom part of my stiffness matrix multiplied by my B1, which is shown there for F2, KSF, that bottom part, times B1, which I determined there. Then hold Control Shift, press Enter, and there's my forces or my reactions. That'll be newtons, newton meters, and newtons. Again, that'll be equal that divided by 1,000 kilonewtons. That will just be into Newton meters. Okay, so there I've solved my reactions, and always, which is good for a quick check, is to check equilibrium once you've completed this example to make sure your answers are correct. Now, just considering my horizontal equilibrium, my horizontal reaction at node 1 is positive 20 kilonewtons, so it's to the right, and that is in equilibrium with my applied loading. And for my vertical loads, vertical load 1 is 13.12 kilonewton, and my vertical at node 3 is minus 13.12, and as you can see, they cancel each other out, so that is vertical equilibrium. And you can also do moment equilibrium, but it's just a bit longer to calculate. But if your x and y or horizontal and vertical equilibrium is satisfied, the moment equilibrium should also be satisfied. So yeah, this is my first frame example. I hope this video was helpful to you. If you have any questions, please ask them in the comment sections below. I will respond to you. And if you like this video, press the like button and subscribe to my channel for more videos. Also, if you have any suggestions on examples you would like to see, please let me know and I'll come back to you. Thank you very much for watching, and yeah, have a nice day.